Hello, good evening. We'll start in a couple of minutes. Alright, I think we can start now. Good evening, everyone. My name is Zumair Hussain. I am a PhD scholar at the Department of Mechanical Engineering at IIT Madras, and I welcome you all to the 11th doubt session for the course of Finite Element Method, Variational Methods to Computer Programming. Just to quickly sum up, we started this course with by the concepts of variational principles, and we expanded that to solve the FEM problem. So in next week we studied the basic steps involved in a finite element method. Then we studied different types of structural problems in 1D FEM. So we studied 1D bar problems, truss problems, beam element problems, and finally, combining all these concepts, we studied a generalized frame element problems. So after that, we started with the 2D FEM, and before that, we discussed some basic concepts of the differential calculus, and then we started with 2D FEM. And 2D FEM, we first studied scalar problems. So we studied a basic Laplace equation for steady state heat conduction. And then we also studied a vector valued 2D FEM problem. For that, we studied a classical example of the elasticity problem. So in last week, we wrapped that up and started with the time dependent problems. So in time dependent problems, our first topic was the eigenvalue problems. And this week we concluded the eigenvalue problems by discussing an example problem of the membrane problem. So we look into this now. So a membrane problem basically, this is a a thin membrane stretched over some boundary. So the governing equation for this problem is given by the following equation given here. So here we have a second order derivative of time, second order time derivative term involved. So just like we studied before for 1D problems, we'll divide the equations, and finally we can write it in terms of the eigenvalue problem. So now we write the weak form of the governing equation and formulate the eigenvalue problems in terms of the eigenvalue lambda. So finally, this equation here would be a eigenvalue problem, and it's simple to get the eigenvalue for this problem. How do we get the eigenvalue? Can someone tell me? How do we solve this further?
Yeah, Umer, actually, this is my today's doubt.
Okay.
Last time also I have given a very strong feedback about this. Actually,
Yes.
the lecturer who is playing with these problems, he has to first solve it manually, and then he should
Yeah, yeah.
proceed to MATLAB. Actually,
Yes.
yesterday when I was tackling the problem related to this eigenvalue, I think that is assignment number 11. It is. So I think actually this del phi I, del phi j. Actually, I didn't get the clarification what this represent del phi I, del phi j. Whether it is at any particular node, or we have to just give the equation form to calculate this integration. What it is. So this thing I want clarification.
Okay, okay, okay. Yeah, yeah. Even I watched those lectures. I also was doubtful initially because these dynamic problems are not very my strong suit. So
Okay.
I also looked a bit into this. So basically, first let me answer my own question. So
Okay.
in eigen, so I'll start with this. In eigenvalue problems, we discretize the domain as usual,
Hmm.
and based on the type of discretization, we get our K and M metrics. So
Yes.
and based on that discretization, we get the
Hmm.
number of the eigenvalues.
Okay.
So we every time we'll discretize, we'll get more nodes. Discretize further, and we'll get more nodes, and then we'll get more number of eigenvalues. And it makes sense, right? There can be n number of eigenvalues. It can keep on increasing, but the the values of, say, if for I have three nodes, so I get three eigenvalues. Then I discretize to six nodes, I'll get six eigenvalues. But the value of those first three eigenvalues would be same. It should be same as the three eigenvalues we got for early three nodes. And as we go on discretizing, the value would the error in those values would reduce. So that is
Okay.
basically the straight logic. And regarding my question, how do we get this? So basically, this if we solve this equation here, what do we have? K minus lambda square m times this vector alpha, right?
Yes.
And this is how we oppose our eigenvalue problem usually. So if you remember this,
Yes.
some vector v is equal to 0. So all what we do is we take determinant of this and we get the lambda.
Yeah.
And similarly, the same thing we do here. We take determinant of this and we find lambda square. So
Okay, so
we take
you were just asking how to get the eigenvalues of matrix.
of an eigenvalue problem. Yeah, we
Okay,
have to
okay,
know both k and m for that.
okay, okay.
Okay, so yeah. So that's how we solve any we solve for any problem. We There can be any type of problem. We just formulate it in terms of the stiffness matrix and mass matrix, and then we do this take determinant of k minus lambda m. Okay, so then here we conclude the section for eigenvalue problems. The programming part was shown in the lecture, so I won't go much into it. We will, as you mentioned correctly, that how to get that manually is not very clear. So we'll try to do that in the problems we solved today. Okay, so next is the parabolic partial differential equations. So in these type of equations, we have uh, say a, a first order time derivative term. If I'll talk in layman terms. Uh, and a classical example of such problem is the transient heat conduction equation, where our the special thing about these problems is that the response or the solution basically smoothens with respect to time. As time passes, the response has to smoothen up. So if you see that you provide a heat flux somewhere at a boundary, then you see
Mhm.
that the temperature quickly rise at that boundary, and then it slowly diffuses, and it will kind of smoothen up. The profile
Yeah.
will become flat. Even if I don't provide any flux, we have this, and we maintain this temperature profile, and we leave it over time. It would gradually grow like this, and it should become flat. So yeah, so these type of equation basically smoothen the responses. So the equation should look something like this. So earlier this was our Laplace equation. This is our Laplace term. Then this is our heat source term, which we saw when we discussed 2D scalar 2D problems. These two terms were there. Now extra term we have is the this temporal term, time derivative term. So so since we have time dependent problems, in addition to the boundary condition, we'll also have the initial condition. So we need to know the initial temperature configuration here. Then the way we take the weak form is same as before. So the first two terms are quite clear. Then for time derivative term, it's straightforward, right? So
Yes.
the difference lies in the way we discretize it, or way we sorry. So a difference lies in the way that we substitute the approximate the function. So
Okay.
we used to approximate the function as some constant times the what do we call that linear combination of the approximation function or the shape functions, alpha j phi j. So phi j used to be a space variable, sorry, a space function, a function which is dependent on the space coordinates x and y. But and the constants alpha j, they earlier they were constants, just constants. But now these constants would have to vary with respect to time. So we break the time derivative part and the space derivative, time dependent part and the space dependent part. So when we substitute this u in this term here, alpha j phi j by rho t, w is of course phi I. So alpha j, so phi j is not dependent on time, right? So we can separate it out for the derivative, and we can just write this as lambda phi I phi j, and the time derivative term can be taken out of this integral because it's space integral. So we'll have j by dot t, which we have written it as here, alpha j dot. So that's how we so in our final weak form, apart from uh, the having the coefficient of alpha, the solution, our solution, we'll also have the time derivative of a solution.
Yes.
So now now we have a time derivative term. So so there are terms which are which are going to change with respect to time. So we need to discretize our equations in along the time axis also. So we use finite difference method here. So the general form of time matching up the time matching approximation is given in equation 2. So where n represents the current time step and n plus 1 represents the next time step, the value of the solution at the next time step. So this was all derivative we did. So derivation we did, and we'll solve. Then we'll find that the equations can be written in this form. So at the end, we'll know the values at the nth time step. So we know the values initially, and
Okay.
we'll have to calculate the value of the solution at the next time step, n plus 1. So we'll consider all n to be known, and we the our unknown here is the alpha at n plus 1 step. So we'll arrange the equation in such a way that we'll solve for this unknown. Okay, I'll tell you a quick shortcut to do that. We don't need to do all this derivation. So if we'll have some equation like this, k, and then we have this alpha plus c, and we have alpha dot. So this is just a shortcut. This would work here, but I won't guarantee it everywhere. But I haven't faced any problem with this so far. So wherever you have any term which you know would vary with respect to time, like
Okay.
alpha here. K, we don't expect it to vary with respect to time. C, we don't expect it to vary with respect to time. Suppose we also assume that F would also vary with respect to time. So suppose we have some heat source term that is varying with respect to time. We'll consider this also changing. So what you do is you write that varying term as uh, it's mu, right? Mu alpha n plus 1 minus mu alpha n, and the this term, alpha dot term, you approximate this as alpha n plus 1 minus alpha n divided by delta t. And same f also, you can replace this at mu times fn plus 1 plus 1 minus mu times fn. So at the end, if you arrange the alpha n plus 1 terms together, you'll have c here, you'll have delta t and mu times k here, and yeah, we have alpha n plus 1. Rest this term would be as it is. This, well, this I write this as f bar, this whole term, and then the rest of term will come here. We'll have we'll have c minus delta tn 1 minus mu k into alpha n, this whole term. So you see, this is the same as this equation here,
Mm, yes.
right? So this is just a shortcut to get to it directly. But you have to be careful on the terms which are actually varying with respect to time. You have to change them, write them in terms of mu and the their their value at the respective time step number. Okay, so yeah, next thing is the choice of mu. What is the choice of mu? So there are various type of method named based on the choice of mu. So the basic uh, basic is we take mu as zero. That is called forward difference method. So this is, I think, also known as the explicit method, where we don't use the value at the next time step. Yeah, something like that. Uh, that's called forward difference method. So this method is not very convenient in terms of stability. So it is stable, but its stability is subjected to some condition. So we'll talk about that. What is that condition? And also its convergence with respect to time step is also linear in terms of time step, unlike the others. And then mu equals to half is known as the Crank-Nicolson method. This is unconditionally stable. There is no condition. It is definitely stable, and its convergence is also good. As we reduce the time step, the error would reduce by square. And then we have 2 by 3, that's called Galerkin scheme, that is also stable. And then mu equals to 1, that is the backward difference, or it is also known as implicit scheme. So this is also stable, and its convergence in delta t by 2. So, so we talked about the conditional stability. So, stability, which is conditional, means that the the time step is bounded for it to be stable. We can't use a time step beyond certain limit. So, at times the condition here is that the time step should be less than the delta t critical, which is equals to 2 upon 1 minus 2 mu times lambda. So mu, mu is this mu, and lambda is the largest eigenvalue. So
Okay.
we need to. I think this was not there in the class, but I thought it would be interesting to share. So
Okay.
you need to, but for this you need to know the eigenvalue. And this is eigenvalue here, but in some problems it is also represented by some other parameters. I think
Mm.
if it's also, it is also given in terms of the diffusion coefficient. That we
You are talking about this mu or what?
lambda.
Diffusion coefficient I didn't see in my career. Uh, no, diffusion coefficient I didn't see anywhere.
For this delta t
Yeah,
critical.
yes.
Okay, I'm not sure. So, but this is standard. Largest eigenvalue. This is standard.
Actually, different companies, when they use their coding techniques to to fix these simulation issues, to fix their convergence rate or what it is, they use their codes according to their countries also. Actually, for
Oh.
example, if you are using any software made by any company in USA,
Hmm.
then what way they will prefer, they will suitably use the all the codes related to ASME.
Hmm.
Okay, yeah.
Yes.
So these things, do you know this CFL criteria of explicit solutions?
No, no.
No, you can search this on Google because if any company is using ANSYS as the solver, then they always use CFL criteria to decide whether this solution should be explicit or implicit.
Okay.
Oh yes,
Oh, that's interesting.
yeah. You can you can search this criteria.
Sure. Okay, so this was regarding the conditional stability.
Yes.
For, for the convenience of others, shall I Google it now?
Ah
So
yes,
that
yes. You
so
can you can.
if anyone is interested, they might also know.
Yeah, 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 yeah.
CFL. CFL criterion CFD.
No, no, no. CFL criteria is explicit methods. You can write directly.
CFL condition, necessary condition. Search here, so I can share the screen also.
Okay.
Yeah, so it is showing. It is
Okay.
essential to understand that the CFL condition is a necessary condition for the stability of certain numerical methods,
Yeah.
particularly those that are based on explicit time integration. Yeah,
Yes.
yeah. So the explicit is we know that that is conditionally stable. This
Yeah.
condition determines the maximum allowable time step size that can be used to ensure the stability of the numerical relation. Okay, okay.
Okay, actually, let me tell you one thing. For example, there is a material testing lab in any company, and they are doing crash analysis. So, crash analysis, we are generally interested to know whether in these milliseconds or these nanoseconds, if I apply some acceleration or some load to our structure, so what will be the response of our structure? What should be the maximum reaction generated at the surface of that structure? So basically, in these particular cases, always CFL criteria has to be satisfied first. This I have seen in my career, but I don't know what could be the other things for these explicit solutions.
Okay, okay, okay.
Yeah.
Yeah, yeah. CFL must be chosen such that the information propagates casually with the distance travel one time being less than I. Yeah, yeah, the okay, the one that I was remembering in terms of diffusion coefficient, that was for some specific problem, and that has to be that is to be related with respect to the mesh size. That is
Okay.
determined. So if we can't just keep on refining our mesh and keep our mesh the our time steps same.
Okay.
If mesh size is reduced, we need to reduce the time step also, and that is there is some condition for that.
Okay.
I can't remember that exactly, but there was something because I was facing this problem in my simulation.
Okay.
As soon as I refined the mesh
Hmm.
and kept the time step same, the results would go nuts. I used to get very uh, random solution then.
Okay. Okay.
I think
But
it's
yeah, yeah, but this this CFL criteria when I have used in LS Diana,
uh-huh.
so whenever it is satisfied, I didn't face any issue in my conversions always.
Okay, that's
Yeah,
nice.
yeah, yeah, yeah.
That should not.
That's why I'm saying if you will go through the different softwares, different modules, those companies are using, and in
Yes.
different countries also, they use their own approaches in simulations.
Oh, yeah. Right, right.
Yeah.
So this is interesting. The information should not propagate faster than physical wave speed in the simulation.
Yes.
Yeah, yeah. So, okay. Our time step should be small enough to measure the smallest change that is occurring in a simulation. That is
Yes.
basic.
Yes.
I think the basic gist of it.
One of my seniors has told me the concept of there is a concept in thermodynamics named as a quasi-static process,
Yes, yes,
and in it is very beginning. It's taught generally in very beginning of the thermodynamics sessions,
yes,
because there also, if you remember, we have approximated our all the processes, either it is constant volume, constant entropy, or what it is. So they should be quasi static first, then we can apply all the thermodynamic conditions of our analysis to the system.
yes,
So, yeah, so this stability criteria is somewhat related to that concept also, I think so.
yes, 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 yes. Yeah.
Yeah, yeah.
Okay, it's interesting.
Yes.
Okay, let me get back to my first screen.
Yeah.
Okay, so this was all about the parabolic PDEs. Next, we discuss the hyperbolic partial differential equations. So here, talking in layman terms, you will see the second order time derivative term, and the special thing about these equations is that the response doesn't smoothens or die out. It will keep on oscillating. So a classic example is the vibration of beams,
Okay.
which we discussed here. So again, we have the classical beam equation here. We recognize the term here. This was our distributed load term, and now in addition we have the temporal term. So taking weak form for this equation is simple as usual. Uh, we and like we discretized before for parabolic PDs, we approximate the solution uh, as a as the linear combination of the approximation function, where approximation function should be a function of the space coordinates and
Mm.
the corresponding uh, coefficients of these approximation function, which were constant earlier in non-time dependent problems, will now be dependent on the time. So we'll just quickly take a look at the time dependent term. We had here 12 m times, so y dot is now tau square by uh, aj pj times tau t square, and w is phi I dx. So since pj is not dependent on time, we can take this term out. So we'll have 0 to L m phi pj dx, and we can take the temporal term out of this space dependent integral. That tau square aj dot t square. So we have, which is written here as aj double dot. So now again we have our equation in terms of the matrices and vectors, and now again we have a term which is varying with respect to time, and that this is a second order derivative term now, a double dot. So we can't use the time margin approximation like we did before. So
Yeah.
this is a little complicated here. So so we use what is known as the Newmark scheme, and so we would discuss this for a generalized equation. So we have a second order time derivative term. We have first order, so this is second order time derivative term. We have first order time derivative term, and we have time independent terms or zeroth order, and then we have our body force term. So these are the approximation for. So we basically need to find the so what we need to do is we need to break this equation one, and uh, convert everything, every unknown in terms of just one unknown. That should be the
Okay.
solution at the next time step, right? Which is
Okay.
basically an plus one. We want everything in terms of this. So we have these equations in Newmark scheme. So for
Okay.
an plus one, that is the displacement at the next time step, the velocity at the next time step, and the acceleration at the next time step.
Yeah.
So so what we do is we substitute the n plus one a dot and a double dot, and convert them in terms of a n plus one or a n, or just a n or a dot n or a double dot n, because the values at nth time step are known,
Mm-hmm.
and the one unknown we have to keep is a n plus one. So we convert this a double dot n plus one in this equation. We write
Okay.
in this form, and we'll see. We just have, this is unknown and this is known, this is known, this is known. Similarly for velocity term, this should be actually n plus one. So this is our unknown, This is known, this is known, this is known. So we substitute these back in our equation 1, and
Okay.
after complicate this complicated manipulation, algebraic manipulation, we'll get our equation uh, in terms of this equation k bar a n plus. So we just have this one unknown,
Yes.
and we can just solve this and get our solution at the next time step. And we keep on repeating process we store this an plus 1 in our variable for an, and then keep on repeating, finding the new value at the next time step.
Okay.
Okay. So one more tricky thing about these problems is that about the initial condition. So earlier in parabolic PDEs, we used to just have just the value of the solution at the for the first time step. We used to have something, and for this is for parabolic. For this is hyperbolic, right? No, for hyperbolic. Yeah. For hyperbolic, we'll be given the value, or I'll write a. Well, I should write no, a. We'll have the value at t equals 0, and we'll have the the velocity at t equals 0. But you'll see that we also need the acceleration at t equals 0, a double
Okay.
dot. So what we do is we have this basic equation, the equation 1 we had. We can substitute the for n equals to for t equals 0, we have this t equals 0, and for t equals 0 we also have this. So we know these terms, these term, this term. We can just manipulate these equation to get our this at t equals 0.
Okay.
So this is just simple manipulation. Okay, so this was it about the time dependent problems. Uh, if there's any doubt, we can discuss it.
Can you just explain it again? What is the difference between these two, as you explained earlier? Here, what is the difference?
Your voice is breaking. Hello,
Hello.
hello. Yeah, am I audible now?
Yeah, now you are audible. Now.
Sorry, I think there was some issue with my internet. Let
Yeah,
me
yeah,
share
yeah.
my screen. Is my screen visible?
Yes.
But it's not visible to me here. Well, let me just fix it. Yeah, it is here now. Yes, please.
Yes. So my doubt was, in terms of initial conditions, you just have explained the basic difference between these two. Can you just repeat the concept again?
Yeah, sure. So in our parabolic equations, we just have first order time derivative term, right?
Yeah.
So we only need one initial condition.
Yes.
That is the where it go? Yeah, that is the value of the solution at the first time step.
Okay.
But in hyperbolic PDEs, we have the second order derivative.
Okay.
So for that, we need two initial conditions.
Yeah.
Where did it go again? Yeah, so we have second order time derivative term. So we need two initial conditions. So one is the display the value of displacement at the initial time step, and
Hmm.
the value of velocity.
Velocity, yes.
Okay. Anyone else has any doubt?
No. So, Umer, based upon this basic conception, can we just regulate these two means hyperbolic and this parabolic uh, functions as per our convenience if we know the boundary condition of the displacement and boundary condition of the velocity and displacement both.
Regulate means
Regulate means, for example, in our problem, we know only the displacement. So you mean to say in that particular situation we have to go for the parabolic and we can't use hyperbolic?
no, 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 no. If so, governing equation and the boundary condition both are both are important part for defining a problem.
Yeah,
we
yeah,
we can't just give an equation and give just one uh, incomplete boundary condition. That would become an
yes.
ill-posed problem.
Okay,
So
okay,
if
okay.
so the governing equation defines the physics of the problem. So based
Yeah,
on the type of
yeah,
problem you're solving, you will have the equation for that, and
yeah,
then you need boundary condition in addition to that.
yeah.
Yeah. So these two are not uh, connected. Like parabolic equation and hyperbolic equation are not connected internally. They are separate thing. Separate equation describing separate phenomena.
No, no, actually, I know this thing. These two are separate, but for application for point of view, we have to decide for which formulation we have to go for. Means
Yes.
what will be the suitable thing. Yeah, that's why I was asking this.
Okay. Yeah.
Yeah,
Yeah.
yeah,
Okay. So if there's no doubt, then we'll just start discussing some problems.
yes,
Okay. So we have a time dependent problem. We'll try to find the weak form and even try to approximate the solution.
Mhm.
So we perform integration by parts,
yes.
and what else we have? We'll have a boundary term, and we'll have our load term. So this will be our weak form, and if
Yeah.
we want to discretize it, we'll do it. So let's say u equals uj phi j, w equals phi I. So we can write this as phi I phi j dx into uj dot. Then we have 0 to L phi I derivative with respect to x, phi j derivative with respect to x dx uj. Then we have 0 to L phi I f dx plus phi I dou u by dou x. So this will be our kij uj dot, sorry, mij. It's usually called mass matrix. Kij uj equals fi. So if we want to discretize this in time marching scheme, can we do it here itself?
Mm, Mij Skij is equal to Fi.
So how do we do it? First, mij is constant. Then how do we do discretize uj?
Mm,
So for derivative term, we used to write n plus 1 minus n upon delta t, isn't it? So the derivative basically means in crude form, it means this only. The value at next step minus the current step divided by the time difference.
yeah, yeah, yeah,
So this can be approximated like this. And kij is again constant. Then uj can
yeah.
be written as mu times ujn plus 1 plus 1 minus mu times ujn. And what about fi? Can we write fi as it is?
I think so
But
because Fi.
in fi we have this f term which is dependent on time. It's a function of time.
Ah, yes, yes,
So it's
yes.
safer to write it as fin plus 1. So you can just arrange all this and write it in terms of ujn plus 1. Oh, sorry, write take all the coefficient of ujn plus 1 together. So at
Hmm.
the end you'll have mij plus delta t mu kij into ujn plus 1. And here you'll have the your fi bar, I'll write, and then plus mij minus delta t 1 minus mu kij
Yes.
into, sorry, this thing into ujn. It should be vector, right? First order tensor,
Hmm.
because it has to be
Yes.
added with fi.
Hmm.
Okay, yeah. So next question is, I hope first question is clear. There's no doubt here.
Yeah.
The next question is, find the eigenvalues for the following stiffness matrix and mass matrix. So what is the technique to find? So we 4
We have to write it as k minus lambda I, lambda square m.
or I'll just go back one step. You have to write the equation as this, right?
Yeah,
So we take determinant of k minus lambda square m.
lambda square m. Yes, and put it as equal to 0. Then we
Yes.
will find, yeah. But
So
it is asking about the stiffness matrix eigenvalue or mass matrix eigenvalue separately, or it is talking about the combined problem of these two.
combined problem. Yeah.
Okay, okay, actually,
That
I
would be
was
different,
thinking,
right? Yeah. That would be
yeah,
different thing.
yeah.
So we have our right. So we'll have 2 minus lambda square 4 minus 1 minus lambda square minus 1 minus lambda square 1 minus 2 lambda square. Okay.
Yeah,
So we have, I'll just write this omega to avoid the confusion of the square. 2 minus 4 omega into 1 minus 2 omega minus, so we have 2 minus 4 omega minus 4 omega plus 6 omega square. We have plus 1 plus omega whole square, right?
yeah,
Plus 2 omega plus omega square. So se- we have 7 omega square minus 8 omega plus 2 omega is minus 6 omega. And what else we have? 2 plus 1, 3, 21. How do we solve this?
21 and 6. Yeah, I think the value will become some imaginary term or uh,
Yeah,
some non-integer term.
let me check if I can get it using calculator.
Yeah,
It's taking a long time. This thing can't solve. I
yeah.
think it should be some
That's
imaginary.
why. Yeah, yeah. That's why I was talking about. I think there is any mistake. Mm, 2
4
minus
AC.
lambda square 4.
Yeah, my
Yeah.
4AC is going to be bigger than 36.
Mm-hmm.
84. 84, right?
One second. Minus one minus omega.
21 into 4. Yeah. Yeah. So we'll get some imaginary eigenvalue and
Actually, you did a mistake. Let's see. After the row, just after this matrix, please see row, second row after the matrix.
yes,
Here you
this
have
side.
written 6 omega square.
Okay, it's 8.
Yeah,
Oh, shit. Thanks. So it should be 9.
yeah.
9 omega square. But that also won't make any difference, right? It would still be
9
imaginary.
3 27. No, 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 no. Now it is meaningful. 9 3s are 27. So 9 and 3, these two are the coefficients.
Oh, yeah, 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 yeah. So we have 9 omega square minus 9 omega
Yeah.
plus 3 omega plus 3 omega plus 1, 3 into omega plus. Wow, it's became so solvable. So omega equals
Again
minus
you did
1.
a again you did a mistake.
So omega minus 1. So this would be imaginary, right? We can't
Yeah.
solve this like this. Anyways, so our lambda equals root of omega, and that would be root of 6 plus minus under root b square minus 4ac. That's 36 minus 36 into 3, 18, 108 upon 18. So these are the two eigenvalues.
Yes.
Okay. Okay, so we'll try to do this thing for coupled equation. So we take the first equation, and so here are two variables are P and the temperature T.
Yes.
Okay. So this is actually the phase field equation. This
Hmm.
is
Yes.
the Allen-Kahn equation.
Is it related to some phase transformation or
Yeah,
what
yeah.
it is?
Yes, this is
Okay.
actually the problem for cooling, cooling of a
Okay.
solid. So this is
Okay.
the heat equation, and as this
Okay.
temperature would go down, the
Mm-hmm.
phase parameter P would change from
Okay.
liquid that is P equals 0 to P equals 1.
Mm-hmm. Okay.
Yeah, I think I have skipped one term here. There was a driving force term also in equation 1.
Yeah.
For
Yeah.
simplicity, I have skipped that.
Yeah.
Okay, so we take a weight function V for first equation, and we have tau dou P by dou T. So this is same as before. and we have our, so we perform integration by parts on the right hand side term and we bring it to the left hand side. We get a plus sign.
Yes. Yes.
Bring this also here. And we'll all have some boundary term. We'll leave that. So
Hmm.
if we discretize, we uh, approximate this, we write V as phi I and we write P as Pj phi j. We write T as Tj psi j. So separate approximation function for T and P.
Yeah.
So we have phi I tau times dou P by dou T is phi j, and we have Pj dot, plus we have gradient phi I dot epsilon times gradient phi j minus gamma times phi I psi j, and then we have, this is, this term is only phi I, other are constant. So we'll just remove the boundary term for now, keep it 0. So we have Kij, sorry, it's Mij Pj dot plus, sorry, we also have the Tj here, and we also have Tj here. Kij Pj plus, we can write this Lij Tj, plus we have Fi term. And for second equation, we'll also, uh, okay, we'll do that later. So we have second equation, write the weak form for this, W dot T by dot T, W, W gradient square T plus W K times dot P by dot T. Perform integration by parts. We have W, this as it is, plus gradient W dot gradient T. We'll skip the boundary term. We have W K dot P by dot T. So we approximate W as psi I, T as Tj psi j, and P as Pj phi j, as we did before. So we have, so W is psi I, T is Tj psi j, Tj psi j. So we write psi j, and we have Tj dot here. Then we have gradient psi I dot gradient psi j tj, and then w is again psi I k into to p is pj psi pi j, right, pi j, and we have pj dot equals 0.
Yeah.
So we have, right, this is cij tj dot, we write this as dij tj, and we write this as eij pj. So now we discretize this with respect to time. So
Yeah.
it's clear that Cij is independent of time, Dij is independent of time, and Eij is independent of time, right?
Mm-hmm.
So only thing that would vary is Tj dot Tj Pj. So we have to approximate this. So Tj dot, it's clear, right? Tjn
Yeah.
plus one minus
Minus
Tjn.
Tj by delta T.
Yeah. Then Dij is fine. So here we have mu times
Yeah. Tj
n plus one,
plus 1 minus
mu
plus
times,
1 minus mu.
right? Then we have Eij mu times pjn plus 1
Yeah.
plus 1 minus mu times pjn. So we have to, now we have two variables, right? Pjn
Hmm.
plus 1
Yeah.
and tjn plus 1. It's coupled problem. So we combine the respective coefficients. First for tjn plus 1, we have Cij, then we
Yeah.
have delta t
Dij.
mu
Hmm.
times dij. That's it, right? That is coefficient of tjn plus 1.
Yeah.
Then we have for Pij, what do we have? Pjn plus 1. So what is the coefficient we have? It's just minus Eij, minus delta t mu times Eij. There is no other term, right?
Yeah.
Then rest we can club all the terms together and just write them as what L is used. Where is this? F G G I, because these are the values at the old time step.
Hmm.
So it's a vector. And again for the above equation, we can do the same. First equation. So we have Mij Pj dot. So I'll just do it. Okay, I don't want to confuse you. I'll do it
Okay.
as usual. So I'll just write it directly. See again, Mij, Kij, Lij. They are all independent of time.
Yes.
Even Fi is independent of time. There. So Pj is again mu times Pjn plus 1 plus 1 minus mu times Pjn plus Lij times mu times Tjn plus 1 plus 1 minus mu times plus fi is constant. So I club the tjn plus 1 terms together first. That's just delta t mu times lij.
Yeah.
Then we have for pjn plus we have m time we have mij, then we have delta t mu times kij. So pjn plus 4. That's all the old time steps solution values we can decide with h I bar. So
So you in this
yes,
step you have eliminated also the Cij term to the right.
which one?
In the last step,
Yes,
you have also eliminated this Cij term to the right hand side.
Cij, this Cij.
Ah, yes.
Okay, you mean in this equation, right?
No, after this equation.
Oh, this is not the above equation. This is this equation. This
Okay,
one.
okay, okay, okay,
So I've
okay.
summed up the. This is equation two actually. This is equation one.
Yeah,
This is equation one here. This is equation two. So even for coupled problems, we can do this. So I just wanted to demonstrate this. How do we do it for coupled problems? Again, we arrange the equations with for the unknown at the next time step for both the unknowns tj and pj.
yeah,
And the same way we use to solve coupled problem, we can assemble the matrix and the right hand side. Okay, so I hope the this was little complicated, but it was clear.
yeah.
Okay, then for the next problem, use the backward difference method for temporal approximation of the previous problem.
Yeah,
So what for the backward difference, what do we have? Mu equals
use the backward difference method for temporal approximation of previous problem. Backward difference. Mm, Actually, I didn't go through this lecture.
no
That's
problem.
the problem. I don't know.
Backward difference mu equals one. Forward
Okay,
is mu equals zero.
okay, okay,
So I forgot that there was an interesting way to demonstrate this using some
okay,
steps
okay.
like this. I don't remember this very well. This is time step n plus one. How do there was a very interesting way I forgot it for to demonstrate what is backward, what is forward, what is Crank-Nicholson.
Okay.
Okay, so anyway, for backward difference, we just put mu equals to 1. So these equations we have derived in terms of mu only. So we can just put mu equals to 1. We'll get the we will get these equations, right? So
Yes.
you see that when you put mu equals 1 here, so suppose you see this equation right here. If you put mu equals 1, we'll be only left with the mu pj n plus 1, and mu pj 1 minus mu would be 0, so pj n terms would go away for mu equals 1, and similarly
Yeah.
for tj n. So we use the value at the next time step. That is why this is
Yeah.
called forward difference method.
Okay.
Sorry, this is called backward.
Backward,
Yeah,
backward
yeah,
it
yeah.
is.
we
Backward.
we use the value at the next time, and from that we do it.
Yeah.
I hope I am not confused with respect to backward and forward. I'll just check the note for clarity. I don't want to confuse you.
No, no, no. You are right now.
Yeah, yeah, backward is mu equals 1.
Yeah.
So in mu equals 1, this is also called implicit. It's called
Hmm.
implicit because we will have the values for the next time step. But if we take explicit or forward, we'll keep mu equals to 0. So this term would cancel here. This term would cancel, and we'll be left only with the value of the last time step.
Hmm.
So here, this complete Kij Pjn would be known, and the only unknown would come from this term there.
Yeah.
So that is actually the gist of this using forward and backward. So
Yeah.
we just put mu equals to 1. We'll have all these equations. Just put mu equals to 1 here, here, here. We'll get these equations the same way. And GI HI, the only thing that we'll have to eliminate will come here in GI HI, are the old time step values.
Ah, yes.
All those would be eliminated.
Yeah.
So we for mu equals to 1 by 3, we can do the same. We just substitute this mu equals to 1 by 3 here. And so here nothing would be eliminated. If we would have taken mu equals to 0, these all terms at the left hand side would have been eliminated, and we'll be left with,
Yes.
and GIHI we won't have to eliminate any term. But with mu equals to 1 by 3 or any value between 0 to 1, we'll have all the terms. We can't eliminate
Yes.
anything. Okay.
Yeah.
So yeah, this is it regarding this. Okay. So if eigenvalues for a FEA problem comes out to be 0, 0.2, 0.5, 1, 1.7, find the critical time step for mu equals to 1 by 3. So
Okay.
just,
So this question is related to the formula you have written.
yes,
And,
yes.
yeah. Yeah. Yeah.
So it was something like, no, it was 1 upon some, 1 minus 2 mu times lambda, right?
Lambda.
The numerator was 1, right? Not 2. I was right
Two.
last time. So we have mu equals to 1 by 3, 1 minus 2 by 3, and lambda is the max value. This is the lambda that we have to use, 1.7. So I just quickly calculated,
Yeah.
2 upon 1 minus 2 by 3 into 1.7.
1.7.
That would be 3.529.
Okay.
Okay, this was the straightforward use of the formula.
Yeah.
Okay, this is going to be complicated. So we have to write the Newmark family approximation statement for A dot, A, and A double dot. Alpha equals to gamma equals to half. So I tried to keep it simple here.
Yeah.
So I'll try to remember it. We had A n plus 1 equals A n plus A dot n, I guess. Delta t times A dot n plus delta t square something. I now I forgot it.
Mm.
Something related to it. This was A double dot n plus 1.
Yeah.
Half. Okay, there was half also. It was not n plus 1, it was n plus gamma. n plus gamma. So gamma is half. So we can write this as half of a double dot n plus 1 plus half of a double dot n. Okay, hope this is visible.
Yeah. What is it at last? Half an.
Yeah, a double dot n. I'll write it over here.
Okay. Okay.
A double dot n plus 1 plus half of a double dot n. Then for a dot n plus 1 we had, I think a dot n only. Oh, I think delta t was there. Oh, no, delta t will come next. Plus delta t a double dot n plus alpha.
Yeah.
So this is again same, half of a double dot n plus 1
Yeah.
and a double dot n plus, no, it was n plus gamma, right? Okay, this is the formula that we had to use, that we already used above. Yeah, so we don't need to worry about that. So at the
Hmm.
end, we just need to write the equation in terms of for a double dot n plus 1. We can use the first equation, manipulate the first equation to get our a n plus 1. Sorry, a double dot n plus 1 in terms of a n plus 1, a dot n, a n, and a double dot n, right?
Yeah.
So we just multiply everything by 4. Hmm. First, right. Okay, so just transfer everything that side.
So in the last step, you have combined all these three. Okay.
Okay, yeah. So I this is equation 1 again.
Okay, okay, okay.
manipulating that.
Yeah.
It's a single dot. Sorry. Okay, so this would be approximation for a double dot n plus 1, and if we'll substitute this the value from here to here, we'll get our a dot n plus 1.
And the one. Yes.
So in the class, this was the direct value for the direct expression for that was written in terms of different coefficient beta 1, beta 2, beta 3.
Mm,
So we
yes.
can substitute alpha and gamma equals half there and get that directly. Like that.
Yeah.
Okay, so you can try this. So we know this solution u1, that u1 means time step 1, and we
Okay.
know k and m, we know delta t and alpha. So we need to find the solution the next time step u2. So what do we have? So what is the parabolic equation? Parabolic equation we used to have. So instead of c, I'm writing m. Okay,
Mm,
m into dot plus k into, just a minute. Okay, so and what else we had? That side we had f. Yes. So if we discretize it, we'll have, so yeah, we'll have m times u at n plus 1 minus u at n upon delta t plus k times. Uh, okay, so I've written alpha here, that is actually mu for us.
yeah.
So I'll write alpha n plus 1 minus alpha un. F is 0 anyway, so set right this 0 here. So we'll have m plus delta t alpha. Alpha is 0, right? So this term would go to 0. So we don't have any term here. We just have
Yeah.
m times un plus 1, and that side we'll have m into un and plus, sorry, minus. delta t 1 minus alpha is 1, so yeah, I'll just skip that. K times un. Okay, so there's no zero here. So this would be our equation to find u2. So I'll just put n equals to 0. So n equals to 1. We'll have m times u2 equals m minus delta t k times u1. So we first evaluate this right hand side thing. So we have this as 1 minus 1 0, sorry, 2 1 0 1 4 1 0 1 2 times delta is t is zero point 0.1. So we have
Yes.
0.1 minus 0.1 0 minus 0.1 0.2 minus 0. Sorry, minus 0.1 0 minus 0.1 0.1, and this is equals 2 minus zero point 0.1 is 1.9 0.90, but this is 1.1 actually. Then we have 1 plus 1.1, 4 minus zero point 0.2 is 3.8, 1 plus 0.1 1.1, 0 1.1, 2 minus zero point 0.1 is 1.9. So we multiply this matrix by u1 0
Yeah.
0.51. We'll have 0.55 here. Then we have 3.8 into zero point 0.5 is 1. Sorry, 1.9, right? 1.9 plus 1.1 is 3.55 plus 1.9, 5, 2.45, right?
Yeah.
So we have the following equation finally: 210, 141, 2 times some unknown x, y, z, 0.553, 2.45. So
Yeah.
okay, so I'll just use calculator for this.
Yeah.
210.55, 1413012, 2.45. So we have u2 equals
Yeah.
0.025 0.5, 9.975. Okay, this is quite close to our U1 solution. See, at the uh, first and last node it changed, and at the middle node it didn't change.
Yes.
Kind of smoothing out, because you see there's no but there's no distributed load, or the source term. F is 0, and we
Hmm.
haven't applied a Neumann boundary condition.
Yeah.
So it makes sense that it will smoothen out. Okay, so I've taken this from one of the assignments to discuss some past problems also.
Yeah.
So we have been given this triangular plate subject to some traction, and we'll try to solve some basic questions from this problem. So first of all, what will be the shape function for this? Can someone answer me here? So we have node 1, 2, 3. So what should be n1?
Node 1, 2, 3. Can you just scroll up
Yeah,
the. Okay. Okay. X plus y equal to 2 minus x minus y by 2, I think.
2 minus,
X minus y by 2, I think.
you meant 2 minus x minus y by 2.
Yeah. No, no, no. Please use this denominator of 2 among the whole expression.
Okay, okay, you mean this.
Yeah.
Okay, okay. Yeah, we'll see. This seems correct answer. We'll see how do we go about that. So n1 is n1 should be any function that should give a value 1 over the node 1, of course, and it should be 0 over the along the line 2 3. So for that it's better we get the equation of line 2 3. So equation of line 2 3 is, this line's equation is
X plus y equal to 2.
x by 2, yeah, yeah, x plus y equals 2. Oh yeah, that's better to write in that way. X plus y equals to 2. And so we know that so the shape function should be equal some constant time, this equation, right? Because
Yeah.
this equation would always be 0 there. And to find the value of alpha, we substitute the value at 0.
0, 0 at
Yeah,
is 1.
at node
Yeah.
1.
Yeah.
At node 1 we have n1 equals to 1,
Yeah.
that is equals to alpha times 2 minus 0 minus 0. So
Yeah.
alpha equals half. So that is correct answer. N1 equals to half of 2 minus x minus y. Then for n2 and n3, we can do the same, right?
Yeah.
N2 should be some constant time, the equation of line 1 3, and
Hmm.
line 1 3 is x equals to 0.
Yeah. It is simply x by 2 now. N2
Yeah.
equal to x by 2.
So and if we substitute the value at node 2, we'll get beta equals to half. I'll just write for others. Anyone will see the notes. So at node 2, we have n2 equals to 1 equals to beta times 2. So beta equals to half. So n2 equals to x by 2. Again for N3 we have some gamma times y, the equation of
Yeah.
line 1, 2. Then we again substitute the value at node 3. We have N3 equals 1 equals gamma times 2. Y equals to 2 here, right? Then we have gamma equals to half again, and we have N3 equals y by 2. So yeah, I hope this was clear. We had discussed this before in our earlier uh, discussions also.
Yeah.
So now we have to evaluate the B matrix. Okay, so B matrix is n1x 0,
Yeah.
n2x 0,
0.
n3x 0. Since we have
0.
only three shape functions, then we have
Yeah.
0, n1y
Yeah.
0, n2y 0, n3y. Then we have n1y, n1x, n2y, n2x, n3y, n3x. And since we don't have any, we are not dealing with the conversion of coordinate system, we don't have to worry about the Jacobian.
Okay.
So we know just write n1x is minus half, right?
Yes.
Minus half. N1y is again minus half. N2x is half. N2y is 0. N3x is 0. And 3y is 0. So we have n1x is minus half, 0, half, 0, 0, 0. Then we have 0 and 1y is minus half. Then we have 0 and 2y is 0. 0 and 3y is, it should not be 0, it should half, right? And 3y half.
Yeah.
Then we just switch the values and write down below minus half, minus half. Then we have 0, half, half, 0.
Yeah.
So this should be our B matrix. Then finally, we have the question: write the boundary condition information matrix. So what should be the boundary condition information matrix? I think this was not the question exactly, but we can do this too, right?
Yeah. Since on both the sides roller support is there, so that's why x displacement of 1 and 3 and y displacement of 1 and 2, these should be 0.
You mean alpha 1 should be 0, alpha 2 should be 0.
Yes.
So x displacement of 1 and 2 should be 0, and y
Yeah.
displacement of 1 and 3. So that means
So y displacement of 1 and 3 should not be 0.
yeah, 1, yeah, 1 and 2 should be 0.
Yes.
So for second node, alpha 4 should be 0,
Yes.
and for third node
Node alpha 5.
5 should be 0, right? So now, how do we write uh, the boundary condition matrix? You remember in the program we used to define the boundary condition information in terms of a matrix.
Hmm.
So how do we write that?
Means you are simply asking about the this displacement vector simply.
Mm, no, 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 not displacement vector. In While writing the program, we used to write the mesh information, right?
Yeah.
In mesh information, we first used to define the coordinate, the matrix in which the coordinate information was there for the nodes, coordinates data.
Okay.
Then we used to
Okay.
have element connectivity matrix.
Yes.
Then we also had boundary information matrix.
Boundary information matrix. Mm,
Okay, so let's say node matrix is, we have just three nodes, right? First is 0, 0, next is 2, 0, next is 0, 2. Connectivity, we just have one row. So we have 1, 2. We take the global as local and we just have to write 1, 2, 3. Nothing new here.
yeah.
So boundary, then we just have boundary matrix. So in boundary matrix, we used to go along each element, and for each element, we used to go along each face. So this row represented the element, and the column represents the vertex. Vertex 1, now we have only vertex till 3. So first, so we started from bottom. This is, say, V1, this is V2, this is V3. So at V1, we have defined the Dirichlet boundary condition, right?
Yeah.
Hmm. So this is going to be tricky because we did it for what? For what? For the scalar scalar problem, right?
Scalar field.
Scalar field problems, not for vector
Yeah.
field problems. In
Yeah.
vector field problem, I think we haven't done this.
Yeah.
We only use the simple zero Dirichlet boundary condition everywhere.
Hmm. Yes. Yes. And in the assignment also the same thing was there.
Yeah, yeah, yeah.
That's why. That's why this thing for me is
Yeah,
clear.
this is this will be confusing, of course. So if we want to arrange this information in terms of metrics, can we do it here? For V1, it has to, it should be in terms of nodes, right? It should we can give the information in terms of node, right? If we know that
Yes.
at particular node a digital boundary condition is right, we can give it -1. So if we have node 1, node 2, node 3, and even for node one node, we'll have two set of data. So for node 1, both x and y are fixed, so we give -1 for both. For node
Yes.
2, we have fixed our y, so that is -1. But in x, we have a Neumann boundary condition. Okay, one and my dash and one are looking like same. So and for node 3, we have in x direction we have Dirichlet boundary condition, and in y direction we have Neumann boundary condition.
Yeah.
Anyway, so there is no
Yes, it is.
fixed way to give this information. It depends on how we are planning it to implement this in our code.
Okay, so this is the matrix you were asking for, boundary condition information matrix.
Y- Yeah.
Actually, I thought you are asking about the values of alpha in terms of nodal displacements along a
Okay. Okay.
particular vector. Yeah, yeah, yeah,
Okay.
yeah.
No. 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 That would take a lot of solution
Oh,
steps.
yeah, yeah.
Anyway, so yeah. So this is the end of the problems that I have. If there's any doubt, we can discuss it.
I want to
Excuse me, sir.
ask you one
Yes.
thing. Can
Excuse me,
you?
sir.
Yes, sir. Please.
Hello. Sir, can you explain the force matrix, particularly F3 and F6, in that surface traction in the triangular last problem,
Okay. 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 Yeah.
particularly F3 and F6?
Okay. Where it go? Here, right. So force matrix. Here it's a distributed load, right?
Ah, yes, traction force.
So what did we had there? We had our force term as phi a times t naught 1 minus s.
By 2 root 2.
Okay. Okay. So this is given in, along this direction, right?
Yeah,
It's better to break it into x and y components, isn't it? That is why we have been given an angle. So how do we break it?
no, this is just 45 degrees, so we can simply write this as the components as 1 by root 2, 1 by root 2.
Tx equals to
Yeah, T naught by root 2.
1 minus x by 2 root 2, right?
Yes,
And ty would be, yeah. So what do we have now? So if you want to write for node 2, say,
yeah,
so node 2, so we'll have, so if you want to write the entry of F3, we'll have phi 2
yes,
times Tx, right?
yes,
So we'll be solving the integral. Phi 2 is nothing but x by 2, and we know the expression for Tx above. So we'll be solving this integral here.
yes,
And for F4, we have phi 2 again and Ty.
yeah, yeah,
And similarly for F5, we have phi 3 times dx. So it should be dy, isn't it? And F6, we have phi 3 into dy.
but the main thing is there in Umair why sir is asking about this thing. Actually, if you will see at node 3, this traction becomes vanishes.
Uh,
Yes.
in node 3, yeah, yeah, right. What
That's
is
why
it?
actually this is we called as the singularity problem in FEM.
Okay, okay, okay. Yeah,
Um,
right.
Yeah,
F3,
you have in the assignment also.
this would this automatically go to 0 if we'll solve this? Dx.
no, it is because if we put the values of x, value of x equal to 0 in tx.
Mm, it's an area integral. No, it should be line integral, right? ds along ds. Okay,
No, it should.
it shouldn't be area integral. This is not right. Yeah, so this should be along dx. This should be along dy.
Yeah, yeah, yeah.
Sorry. This is same thing. Dx. This should be along dy. This is dx dy. So I think dy at y equals to 2 to 1 minus root 2. It's not going to 0, right?
Yeah.
It should go to 0.
Yeah, if we simply put x equal to 0 in tx, then you can find, because the x coordinate of this node 3 is 0.
Yes. Ah,
And
yes.
if we put the x equal to 0 here, tx, then t naught by root 2 is remaining still.
Yes.
Yes, so I think this thing can be used to evaluate this integral here.
Okay, yeah. So F3 here.
No, I think sir is saying something.
Sir,
Yeah, no, no, sir, you continue. Yeah.
Okay, okay, okay.
yeah. So I hope I couldn't clarify much, but Aman sir had
No problem.
said a lot of right.
No problem. Yeah, that assignment questions we have that.
Yeah.
So particularly in that you have to find the answers. There is no
But
options.
yeah, yeah, actually options
Yeah, there
were.
was no options, right? That was filled.
Yeah. But Umer, you can evaluate here. You can evaluate here. Uh, if you
Yeah.
want to do this, you can evaluate
Sure.
here. Let me clear this thing. Yeah.
Sure. So for F3, right? F3,
F3.
so F3 would be integral in x direction, 0 to 2. Uh, it should be from 2 to 0, right?
Yes.
Because the element is from 2 to 3, is it?
Yeah,
It's
yeah, yeah.
it should
Yes, it
be
Node
is.
number. Yes.
2 to 0 and x by 2 times dx is t naught by root 2 1 minus x by 2 root 2 dx. Do we know the value of t naught here?
Yeah. Let me tell you.
Or just directly we can calculate?
T naught is 1,000 Newton per meter.
1000
Newton per meter.
into x divided by 2 into root 2 into 1 minus
X by 2 root 2.
x by 2 into 2. T limit is 2 to 0. It's minus 373.
What's the answer?
Minus 373.773.
One sec. No, it's wrong. F3 is okay. No, but still answer is wrong because there is an expression written here F3 equal to x into T naught and the value of x is 0.63 to 0.67.
0.63 to
67.
0.67.
Yes.
Even with sign, it doesn't matter, right? We change the sign. Are we sure about this breaking of T like this, components of T.
Yeah, actually, I did the same thing when I was doing the problems in solid mechanics also. Even if we have distributed loads, yeah, but actually, Umer, there is one more technique. If we don't want to split this load here, you can write this as the equation of x and y relation. For example, equation of this line AC is x plus y equal to 2.
Yes.
And if you want to write the integral along this s, you can directly do that dx into 1 plus dy by dx square. Means ds will be equal to dx into under root 1
Yes.
plus dy by dx square.
Yes. Yes.
You can directly use then that thing to here.
Mm-hmm. So we'll have to.
Actually, this answer I also not getting it yet. How this answer was calculated correctly, 0.63 to 0.67. I didn't get this thing.
Okay. So I'll take a look into it. Maybe we'll discuss in next class.
Okay.
I'll take a note of it. Okay. So do we have any other doubt now?
Actually, I have a strong doubt while defining the components of a stiffness matrix used in the just previous assignment, like week 11 assignment.
Okay.
If
I think
you,
for
if you
11th, the due date is not over it right yet, right?
Tomorrow,
no,
tomorrow.
actually
Yeah.
tomorrow is the due date.
Tomorrow is the due date.
So I don't even think we can discuss the due assignment directly here.
Okay, okay, okay.
So
After.
we can discuss it next week probably.
Actually, I am not getting the actual way to find the values of the elements of a stiffness matrix manually. So that's why I was asking.
Okay.
Okay, can you just define one thing? I am asking you indirectly. The expression used in the stiffness matrix c square into del phi I dot del phi j.
Hmm. Yes.
So in that particular, we have to evaluate this integral along with c square by putting the values of I and j directly in the del phi I del phi j, or we have to keep it as the function of x and y, and then we have to calculate the integral over the area.
The
Because
c square is constant, right?
yeah, these
C square is constant, right?
yeah, c square is constant. C square is t by rho, t by rho.
Yeah. Yeah. So you have an integral. You mean your kij is this c square grade phi I dot
Del
grade phi j.
del yeah phi j.
Oh, integration over this area.
Yeah.
So you'll have k11 as c square.
Del phi I, del phi 1,
Okay. 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 So, so grade phi I is what? So grade phi 1 is what? Yeah, yeah, it's the dot product, right? So grade phi 1 is phi 1 comma x, phi 1 comma
yes,
y, right?
y, yes.
So k11 would be
It will be simply the square of this,
phi 1 comma x square
yes,
plus
plus phi 1 y square,
phi 1 y square.
yes. And it is d, yeah, dx by.
So, so what's the issue with this?
No, actually, I wanted to ask you when we will calculate this stiffness matrix elements from here. So still phi 1x and phi 1y, we know these functions. So in this step, means prior to this step, we have to simplify this by putting the values of node 1 coordinates here, or we have to keep it as a function of x and y, and then we will integrate it over dx and dy.
Yeah, we have to keep it as a function of x and y.
Okay, okay, okay,
Yeah,
okay, okay. Actually, my answer was not matching when I have calculated. But yeah, let's see. Tonight I will do it also.
sure, sure.
Yeah,
Okay. So, we can we conclude the session now?
yeah,
All right. So, thank you so much for joining. We'll meet again next
Thank
week.
you, sir, for thank you very much for your nice presentation, sir.
Yeah, thank you so much. Thank you for attending, sir.
Thank you.
Okay. Thank you. Bye.
bye. Okay, bye.